All right, we're gonna do arc length today. And we're gonna start with the distance between 2 points. In 2 dimensions, the distance is the square root of x1 minus x2 quantity squared plus y1 minus y2 quantity squared. And we're assuming that the points are, let's put a comma here, assuming points are x1, y1, and x2, x2, y2. All right, in 3D, the formula is longer, but very much the same, x1 minus x2 quantity squared plus y1 minus y2 quantity squared plus z1 minus z2 quantity squared. And in this case, we are assuming points are x1, y1, z1, and x2, y2, z2. Okay, so that is the distance between the 2 points. Let's ask why we have those formulas. So why? Well, the first formula is a direct consequence of Pythagorean theorems. Well, Pythagorean theorem. I don't think there's a need to show that. The question is why in 3D we still have the same square root and squaring. Somebody could think, why don't we cube or take the cube root instead? And the explanation is very geometric. So let's say we have a 3-dimensional space, and then we go x units in the x direction, and then y units in the y direction, and z units in the z direction, and we want to find this distance, which we're going to put as a question mark. So this is the x units, y units, and then this is going up z units. There's a 90-degree angle between the x distance and the y distance. So let's label this as a point P, and we want to find the distance from the origin to the point P. The origin has coordinates 0, 0, 0. So first, we may find this diagonal, this hypotenuse. This is a right triangle there. And so this distance on the floor will be the square root of x squared plus y squared simply by Pythagoras. Okay, so there's this. And now this diagonal on the floor makes a triangle with this height, with this z, and this distance from P to the origin. And we have a right triangle that goes this way. So this is a triangle down here that I'm showing, P, origin, and this point on the floor, the projection of P down to the floor. And we know this distance already, it is this. And we know Z, which are the 2 legs of this right triangle. So the distance that we're looking for from P to 0, or from 0 to P, which we can label, so this distance is going to be the absolute value, or the magnitude of P, is going to be the square root of this leg squared, which is going to be x squared plus y squared. This is the leg, the length of the leg, but we're going to square it, so we lose the root, put it in here, and then we're going to square this other leg, plus z squared. And that's how we obtain this formula. Of course, this is the formula for the distance to the origin. If you want to find the distance between 2 points, all we have to do is shift by one of the points, and the shift is done by subtracting coordinates. And that's how we obtain that formula. So this is very, very geometric. One thing I want to emphasize is if you have 2 points, say P and Q, in space and you want to find their distance, the way you find the distance, the positive distance, is by doing magnitude of p minus q. And of course, that is going to be the same thing as the magnitude of q minus p. Either way, you're going to end up, as long as we do magnitude, it doesn't matter. We're going to end up with a positive number because the root, well, the squaring of the coordinates or the difference of the coordinates is going to create positive numbers. And of course, every time we write down the square root without any symbol before it, we mean the positive square root. So this is a super quick introduction of distances. Now, what we are after is arc length of a curve. So if you have a generic curve, we want to find the distance. Let's label this as r of t. And so let's pretend r of a is here and r of b is there, assuming that a is less than b. And we want to find the exact value of this distance, which is not the same necessarily as the distance straight from here to here. Usually straight is shortest, but the distance on the curve is many times going to be longer. So that's what we are after. R of t, well, what we're going to do is split this into little bits of distances, itty bitty tiny bits of distances. So this, for instance, will be a generic r of t, while one right after, that doesn't make sense, one right after, but one that is a little bit to the forward direction is going to be r of t plus a little increment of t, so t plus h. And what we're going to do is approximate this distance with the straight line that joins them. So exaggerating, this is not very curvy, but if it was very curvy, there's one point, there's another point, and we're going to approximate this distance with the straight line. The reason why we want to use the straight line is because we have the formula for straight lines, for the distance, the lengths of segments. These are the same things as lengths of segments. So we want to find this distance, which is pretty easy because we already have a formula, and we're going to approximate this curve with this. Is it very accurate? No, but as we move closer, the points closer to one another, this is going to be more accurate to that distance, not to the total distance, of course. We have to split this into more pieces. And the closer the points, the more accurate we will be. We will have a better and better approximation to those little distances. Of course, we have to add more distances, but that's okay because we can take limits. All right. One thing we want to start with is by stating what r of a generic t is, and that's going to be just x comma y comma z, just a generic point on the curve. R of t plus h is not going to be x plus h comma y plus h comma z plus h. That is not true. I want to emphasize that that is not going to happen. We cannot expect that if we add h, then each one of the coordinates will be added in the same amount, because this is curving who knows which way. It may be curving a little more towards the z or more towards the x or more towards the, who knows. Only in very, 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 very special circumstances we will have this kind of situation. But generally speaking, that's not going to happen. So please, we're not going to have that. What we will have is that x is going to be increased by its own difference, and y is going to be increased by its own difference, and so is z. Z is going to be increased by its own difference, its own little number, which we're going to call delta x, delta y, and delta z respectively. And those numbers are not necessarily equal, and they're different. Let me clarify a few things. So delta x is one symbol. It's not made up of two symbols. It's, well, it is not two symbols. It is only one symbol. It is, this is a call name of this variable. Delta x is its full name, and we cannot break it up. It is a little bit like sine of x, for instance. So the name of this function is sin, and we don't break that up. There's a joke in mathematics that says if you divide by n, then you get the number 6. That's a joke. If you cancel the n's, then you end up with six. Of course, that is wrong. Yeah, yeah. Ha, ha, ha. Anyway, so no, the point I'm trying to make, delta x is one symbol. And the reason why I want to emphasize that is because we're going to put squares in it. And I'm not going to necessarily put parentheses, but we understand that we are squaring these one symbol, delta x. We're not squaring the x, we're not squaring the delta, we're squaring the one symbol, the one quantity that is represented by delta x. Yeah, so just be aware of that. The same thing happens with differential. Yeah, dx is one symbol. It is not really two symbols. It is one variable, dx, and delta x are one variable. Okay, so when we subtract the two, remember, we want to find the distance between those two. Let me back up a little bit. This is the original problem. We have r of a, r of b. This total distance we're going to label as s. I'm using this s because if I use the other s, it may look like a 5. So I'm using this s instead. And then if we have a little bit of it, so the big S is all of this from there to there. And the little bit of that is going to be labeled as delta S. Again, this is one symbol. It's not delta times S, it is delta S. So one little bit of it, which is this distance along the curve, is going to be represented with delta S. Now, delta S, we don't know what it is because this is curved. We don't, if we are insistent working with a curve, this is a redundant problem. You know, we want to find the length of a curve. We split it up into little curves. Well, we still have the same problem. We have to find the length of that little curve. So what we're going to do instead is we're going to find the distance across the curve, a secant distance, a segment that is straight. And the way we find that, as I mentioned on the first page here, if you have 2 points or 2 vectors, the way you find the distance between the two is subtract them and then find the magnitude of the subtraction. So we're going to do that. We're going to subtract this guy minus this guy, which is the same thing as this minus that, this point minus this point. And that's going to give us the straight line across. It is not going to give us ds. So I'm going to change the symbol here. Instead of equal, we're going to be putting an approximation symbol. So that is about r of t plus h minus r of t. Magnitude of that, this is r of t plus h, this is r of t. I don't think you want me to necessarily write one next to the other. It is reasonably clear that if you subtract coordinates, so this coordinate x plus delta x minus x, that is going to give us delta x. And the same thing here, and the same thing there. So when we subtract those two vectors, we're going to end up with the magnitude of the vector delta x comma delta y comma delta z. And we know that that magnitude is the square root of delta x squared. Now you know, delta x is one symbol. It is not two symbols. It is one symbol. So when I square that, I don't have to necessarily put parentheses because we know we're squaring the whole of delta x, whatever that is, plus delta y squared plus delta z squared. So the delta s is approximately the square root. Now, if the 2 points are very close together, the difference is very, very small, almost negligible, not quite negligible, but almost. And the closer they are, the more negligible they are. So from here, we can conclude that S, which is going to be a limit, I'm going to put a box because there's more stuff going on there, of the sum, and I'm going to put a box here. There's more things going on, but I don't want to dwell on those, of little delta S's. So by adding little bits, tick, 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 we're going to be able to get the actual length, total length, if we take the limit as the number of pieces goes to infinity. That's one, assuming that the pieces are spread evenly according to time. There's a couple other conditions, but I don't want to dwell too much on that. This is exactly equal to the integral. Again, there's some limits here. And then this delta S, when we take the limit, becomes ds. So really, S is the integral of ds, which makes sense. If you integrate in any integral, the differential and the integral are going to sort of undo each other, and we're going to end up with S itself. All right. But this formula is accurate. It is correct, but it is not very usable because it relies on the variable S, which is what we're after. This is very redundant. So even though it is accurate and it shows the correct thinking, it is not usable. So here's where we're going to introduce this part. So what we really want to do, so S is really, the integral, let's put here some boxes, of dx squared plus dy squared plus dz squared. But here we have a problem. We have no differential. We have to ask, where is the differential? We cannot integrate without a differential. It doesn't, not the way we know how to do. The whole definition of an integral is a limit of a Riemann sum. So we are going to multiply pieces of functions with little deltas, but here there's no deltas. This is a one-dimensional integral. The problem comes, it is derived from a three-dimensional problem, but the integral itself is one-dimensional. It's one quantity. So how are we gonna fix this? We're just gonna use a little bit of algebra. It turns out that if you have delta x squared plus delta y squared plus delta z squared, we can multiply, so that is precisely equal to itself, delta x squared plus delta y squared plus delta z squared, multiplied by delta t over delta t. Okay. Those are quantities. We're not using differential. These are actual deltas, so actual pieces. We're multiplying by 1, so that is not changing the original distance of little segments. We're going to move this delta t into the root, and we know that every time you move something into a root, you have to square it, and we can distribute. So this is going to be delta x over delta t, and the delta t gets to be squared, plus delta y over delta t quantity squared, plus delta z over delta t quantity squared, and then this delta t remains outside. So we move the delta t inside the root, the delta t outside the numerator stays outside of the root. Okay, so this s, which is equal to the integral of that, can be replaced by the integral of this after we take limits, because this is without limits. These are just the actual pieces. So thus, S is equal to the integral of square root of derivative of x with respect to t squared plus derivative of y with respect to t squared plus the derivative of z with respect to t squared. And then this delta t turns into dt. Everything is accounted for. And furthermore, in an integral, we have that the differential declares what the variable is. So this tells us that the variable of integration is t. So this declares variable of integration to be t. Excuse me. So in the original problem, we were assuming that the first point of the length we're about to find is found when t is equal to a, and the last point is found when t is equal to b. And consequently, we're going to integrate from a to b. And so here is our formula. Ta-da! There is the formula for the arc length of a curve. Let's do an example. So let's call this example 1. We're not going to do example 1A, 1B, and 1C this time because this is going to be a fairly long example. So R of t is going to be t squared, t squared. So, and t is going to be run from 0 to 3. Let's kind of draw a quick sketch of this. This is not a parabola, even though there's t and t squared in it. So 0, 0, 0 is the first point on the curve. And then we go 1. So 1, 1, 1. It's not going to fit in here. So this is going to curve to this point. So this is a second point. I didn't say the second point, a second point. If t is equal to 1. And then if t is equal to 2, we're going to go 2, and then 4, because 2 squared is 4, and then 4 up. This is supposed to be concave up. So this is supposed to curve this way. And then there's going to be 3. So this is 1, 2, 3. And then we're going to go, well, this gets tricky because it's going to go all the way to 9. And then we're going to go up to 9. So this picture is too small for the numbers we're going to reach if we want to keep things in scale, to scale. But we're going to have a sort of a parabola. It is, so if we project this onto the YZ axis, we will have a nice regular parabola. The x equals y squared, or in this case, z equals y squared. But we're going to have a lift towards the x axis. So this is going to be a parabola that is going to go, that is going to open, and it's going to come this way. If we project, yes, we're going to, if we project the points, we're going to into this YZ axis, we're going to obtain this parabola, but this is going to have a little bit of a three dimension. It's going to come off the wall. Yeah. So that's the curve we want to find the length of. So the last point, let me do another picture here. So pretend we go this way kind of thing. And this point is going to be 399. And this point in the beginning is going to be 0, 0, 0. And I want to know the exact length of this guy. Of course, this is going to be more than 9 because just to go from here to here, there's going to be 9 units. To go from here to here, there's going to be 3 units. And then from here to here is 9 units. So the answer is going to be longer than the distance from here to there. Let's just find that distance. I'm always curious about this straight distance because it gives me an idea of what to expect at least. So that distance, if we were to go straight, would be the square root of 9 plus 81 plus 81. So 162, 171. And I have a calculator here. 171, the square root will be about 13.08. So this is about 13.08 units straight, but this is curved. So of course we're going to have, so sorry, you guys couldn't see this. So this is the distance. We're going to have more than 13.08. If we don't get more than 13.08, I'm going to be wrong. Okay, so how do we find the actual length? Well, let's use the formula that we just came up with back here. Remember the formula? Take the derivative of x, square it, derivative of y with respect to t, square it, derivative of z, square it, take the square root of all of that after we add together, go from the first t value to the last t value, and do the integral with respect to t. So s will be the integral from 0 to 3 because that's the first and last t value. This is not very clear. There it is. And then square root of derivative of t is going to be 1. When we square that, we're going to end up with 1. The derivative of 2t is going to be, rather, the derivative of t squared will be 2t. Square that, and we get 4t squared. Plus, the derivative of t squared is 2t. Square that, and we end up with 4t squared. And then we're going to integrate with respect to t. That's exactly what the formula says. Take derivatives, square them, add them together. So I squared them already by the time I'm adding them together. And then take the square root, slap a dt at the end, go from 0 to 3 in this case, we're set. So now the rest is computations. 0 to 3, square root of 1 plus 8t squared dt. We can set change of variable. If u is equal to square root of 8t, which by the way is the same thing as 2 times square root of 2t,